This is the Pure Maths 2 paper from 2020, just regular A-level maths. Trapezium rule comes up first. The formula is in the book here. H is b minus a, which is this minus this, as it says here. And then n is the number of trapeziums. There'll be one trapezium here between this and this. There'll be one here between this and this. One here and one here. So that's 4 trapeziums. So n is 4. Get h is 0.5. Now you're ready to put everything in here. y0 and yn are the first and last y's. And then the other y's here, being times by 2, are just the ones in the middle. So we end up with this, and we type it onto the calculator, and we get this here. Deduce an estimate for this. Now, this is the same as this, just with a 9 here. So let's take that 9 out and write it like this, maybe. So because these are both underneath square roots, just like root 2 times root 3 is root 6, I could just multiply those things together, which would be this. This is fine. Root 9 is just 3, though. And of course, I can just bring the 3 out and say this is 3 times the answer I had here, which is 4.5. I think I used ands from before, times by 3, and that's why that 1 is there. But anyway. Comment on the accuracy, if this is equal to that, well, it's accurate to, what, 2 significant figures? So, yeah, just say that. That's all you need to say. Question 2 then, P, Q, and R on a straight line. Now, if you don't draw this, I think it's quite hard to see what this is saying. So I just randomly put P, Q, and R somewhere, like this here. And okay, it says Q is 1/3 the way from P to R. So this journey here is 1/3 of this journey, and this is 2/3. So therefore, I think this, if we doubled it, would be this. So I think PQ times by 2 is QR. But PQ, of course, is just minus P plus Q, and QR is minus Q plus R. So we can do that, and then we can, of course, expand out. We can collect some Q's together and divide by 3, and we end up with the answer. Just draw the picture if you're in any way unsure. Here, let's move this 2 up to the top first, following log laws, and now we can just cancel the logs out and make this. And now we can expand this out. Remember, that's this thing times itself. It's not just 16 minus x squared. For people who need that sort of intervention and just need to hear that. We then, of course, deal with that and we get this. This factorizes. You could, of course, just shove it straight in the calculator and get these, but otherwise, you get these 2 responses here. Now, 8, if we put it in here, makes 2 log of minus 4. And you can't take the log of a negative. Logs can be negative, but you can't take the log of a negative. And so the only solution here is going to be x equals 1, and x equals 8 is not one of the solutions. Good. Question 4 then is some binomial. You get given this in the formula book. This is how to do a binomial with n is a whole number. You later get told how to do it with that one, but now we'll just use this because it is. So of course, if I expand this out, it's going to look roughly like this. 2x I've just replaced with the b. So every time a b comes along, I'll just write a 2x and a 2x squared and a 2x cubed and so on. And now I'm only really interested in this one here. So 7 choose 4. Of a cubed, 2x to the 4 is 15,120x to the 4. The x to the 4s obviously I don't need, they can just go away. And 7 to the 4, they even told you how to calculate as if you didn't just have a calculator type 7 choose 4 and 2. You get this, you cube root, you get this, and we're done. Question number 5 then, so using algebra, or I don't know whether I'm going to manage that. My algebra is not too good. Let's solve, so this makes equal to this, I guess. Now here you can just say this is 2 to the x times 2 to the 1, because you would add these together. If you're doing this, which would create that, and of course this is just 2 lots of this. This is 3 lots of this. So if I just add 2 lots of 2 to the x to both sides, I get 5 lots of 2 to the x is 15. Divide by 5, and then just do log 2 of 3, and you get your answer. 6 then, so most of people would do polynomial division for here. I absolutely despise polynomial division and will refuse to do it at any time. And so what I did instead was I just wrote this thing like this. If you want to watch some polynomial division, just in the bar above this video, type polynomial division, and you'll find examples like this. But anyway, the way that I did this is I just wrote it like this to start with. And where the hell am I going with this? Well, I'm just going to try and create this thing on the top here. So, I need another x here to make an x squared. So I'll just drop an x there. I want to make 8x. Currently, I have 2 x's here. So let's put another 6 here to make 8x. Of course, 2x plus 6x would be the 8x. Now, if you expand this, you get plus 12 at the end. And I want a minus 3, so I'll just shove a minus 15 down there to make that into a minus. And I think this all makes this eventually. Now, why am I doing this? Well, because I'm going to split this fraction here to create this. And then this will cancel with this. Oh, I'll just end up with this, which I think is what they want me to get. So a is 1, b is 6, and c is minus 15. Hence, using algebraic integration, find this. Okay, I'm just going to replace this fraction here with this thing here. And we're just going to integrate, right? That integrates to x squared over 2, that integrates to 6x. This integrates to 15 log of this thing here. The derivative of this is just 1, so there's no fixing to do here. Put in 6 and put in 0. I mean, your calculator will just do this from this point onwards, but I mean, sure. The only thing, if you're not doing this with a calculator, you just need to say log of 8 can be written as log of 2 cubed, and then the 3 can come down to here, which is what allows you to collect these together and get it in the form like this. Question 7 then. So I just mentioned how I hate polynomial division. I also, with even more of a passion, hate quotient rule. So I'm just not going to do it. I'm just going to split this fraction in the middle and just do this term divided by this term. 4 divided by 2 is 2. And x squared divided by x to the half is x to the 1.5 because you take away the powers. Likewise for here, 1 divided by 2 is a half. X to the 1 divided by x to the half is x to the half. And then just leave this alone. Now we can differentiate, of course, got a nice form. Log differentiates to 1 over x. That all works out. And now I just need to fix this until I get something that looks like this. So I tried to make the x's on the top here all match. So if I factorize out an x, then minus 1.5. Minus 1.5 plus 2 is a half. Minus 1.5 plus 1 is minus 0.5 or minus a half. And minus 1.5 plus a half is minus 1, which is what this is. So that's good. Now I can try and make the coefficients match with this. And I'll do that by factorizing out a quarter. Because if I get rid of this quarter, I'll just get a 1 there. So if I factorize out a quarter, it will look like this. A quarter times 12 is 3. A quarter times 16 is 4, so that's good. It's good to go. And now I'm pretty much done here, right? I'm pretty much done. I can write this thing here as this. Minus 1 plus minus 0.5 is minus 1.5. And then I can just take all of that stuff and put it on the bottom. And now, of course, I can just write all these things as roots. If I see a power of a half, I'll just write it as a root. And I end up with what they wanted me to get. There were better ways of doing that. Using quotient rule is not one of them, just because it never is. This is a really interesting question. So it's telling me, so x coordinate of p. Now, p is a stationary point, so dy by dx is 0. So I know this thing has to be 0. Now, it's telling me to write this in this form. So I need to rearrange for an x, except I'll leave an x over here. Now, it's not immediately obvious where to make progress, aside from the fact that you can just times both sides by this, you make it go away, and you end up with this. Now, how do we make this into that? Well, what you can do is you can do what's called cheating, where you start with the thing that you're aiming for. Now, if I raise both sides of this to the power 3 over 2, 2/3 times 3 over 2 is 1, so I just get all of this to the power 1, which is just itself, and this to the power 3 over 2 is just itself to the power 3 over 2. Now I can times everything by 12. No, I can't. I can, what have I even done? Times everything by x to the power of a half. And I've done that because I'm trying to get back to here, so I needed some x squareds and stuff, and some root x's. And now I think I can times everything by 12. And now it's fairly obvious, I think, how to get from here to here. You just, it's basically already there, isn't it? You just move this to the other side. So okay, let's do this backwards then. So now that I've got this plan here, let's do it. So let's do this, move these two things to the other side to get this line with a root here with, it's the same thing, right? And then divide everything by 12. And then the complicated step, divide everything by x to the power of a half, which I think makes this. And then I can raise both sides to the power 2/3. And I think I end up with that as they wanted me to get. Good. So use the iteration formula. So x2 is when n is 1. So you get this. And then x1 is apparently 2. So you type this into the calculator, which gives you this. And then you replace this 2 with your ands. And you press equals a bunch of times until none of the decimals change anymore. And you get this number here. Question 8 then. So f dashed of x is this. So let's just integrate and we get this. So raise the number, divide by 3, raise the power, divide by 2. Remember the plus c, do not forget the plus c, of course. The y-intercept of this is minus 12. Now, that just means this number is minus 12, so that's very helpful. So we get this. And now x plus 4 is a factor. By factor theorem, that just means that f of x minus 4 is 0. So let's put minus 4 into this, and we'll say that's set to 0. We can just type most of these things into a calculator. We'll rearrange it to solve that, and we'll get this, which means our final answer is this, and we'll have the question entirely done. Good. So we have this formula here, initial temperature, so T is 0, theta is 18, T is 10, theta is 44. You can put those results into here. Of course, when you put in T is 0, that all becomes 1, so that's quite nice. The other one's not so nice, but here we can do this one minus this one, probably, to get this. That's that equation minus this equation. You could actually just type that into a calculator to get a decimal and then put these simultaneous equations into your calculator. But if you want to do it the proper way, it's this minus this to get this. Of course, minus b is plus b. Factorize out the b, divide by this object here, and you get b as this. And then you can just do 18 plus that to get a, and you get this, which is this. And now, sorry, which I never actually wrote out, which I should have done. I should have written theta equals this minus this e to the power minus 0.07. Anyway, now that you've got theta is 78, the problem here is that this is always positive because exponential is always positive. So we're always doing 69, nice, minus this number here. and you're never going to be able to get to 78. So this model will actually never reach boiling point. So it's a terrible model because it's trying to measure something reaching boiling point and it's just never going to do it. So what a terrible model. Anyway, this question here is quite interesting. You use the thing from the formula book here, and you're like, well, okay, to find cos of 3a, you could replace this with 2a and this with a, because cos of 3a is cos of 2a plus a, right? We can all agree on that. And now we just use the formula for this. So all of every first bit becomes a 2a, and every second bit just becomes an a. And I think you end up with this. If you have a plus here, you use a minus here for the cos one. So I think we end up with this. And now, of course, you can just do it again. You can say, okay, cos of 2a is cos of a plus a. Down here, sorry, a plus a. So just replace all of these with a's, and just you get this. And sine of 2a is sine of a plus a, and just replace these two objects with a's, and you get this. Now, if you just know the results for cos of 2a and sine of 2a, good, you should. Like, that would be very helpful. Of course, this is just cos squared, this is sine squared. This is just two of the same thing, notice, so you can just do that. You can look at this and see that you're wanting to get everything in coses only. So you can write this as 1 minus cos squared. You can also expand out this, which gives you a sine squared, which you can then write as 1 minus cos squared. And now finally you can expand everything here, and you can collect together, and you end up with the thing you wanted to get. Good, hence solve this. So 1 minus what we just got is going to be sine squared. Of course, I don't want this sine squared, I want 1 minus cos squared one more time. So we get this. We rearrange, we can factorize out cos. We can notice this factorizes. Just imagine this in your head as 4x squared minus x minus 3. And I think you'll realize that it factorizes to this without too many problems, because you get a minus 4 cos here and a plus 3 makes this, and then yeah, that works out fine. And so our solutions are cos of x equals 0, 4 cos x plus 3 equals 0, or cos of x minus 1 equals 0. Draw the cos graph really quickly. Between minus 90 and 180 we're looking here, just between here and here. Cos of x equals 0, of course, is just when we're at minus 90 or 90, so that's nice. Cos of x equals 1 at 0, and that's the only time between these two values that it equals 1. And here, just take away the 3 divided by 4, get your primary solution of 138 degrees, so if minus 3/4 is down here somewhere, that's the solution your calculator just gave you. But of course, looking between minus 90 and 180, that's the only time this intersects the graph. The other intersections are further than this and further than that. So I think 1, 2, 3, and 4 are the only answers that we have here to do. So the mod function question then. So the key thing about mod functions, firstly, we've got to find this point here. Now this point is called the cusp of this, when it does this kind of corner thing here. What a description that was, by the way, can I just say? Anyway, so this is when the behavior of this mod is changing. And the behavior of this mod changes when x is minus 4, because that makes the mod 0. And then beyond that, the mod times it by minus 1 or whatever. So x is minus 4, just because that's when this object changes behavior. Of course, when x is minus 4, you get 0 here, and you just get y is minus 5. So you get this point here. Now, talking about that change in behavior, what the mod function does is if x is above 0, or equal to 0, I should have put equal to 0 here as well, the mod function does nothing, right? It just leaves it. So the mod of 5 is just 5. If the input is less than 0, like minus 5, the mod just times it by minus 1. And minus 1 times minus 5 is 5, and you get a positive number, which is how we always think about mods. We always get positive numbers. So essentially, what I can do is I can just replace this x here with x plus 4, and just write the rules the same. So x plus 4 modded is x plus 4 if x plus 4 is greater than 0. So I've just replaced x with x plus 4 here. But of course, solving these, we get this and this. And so this function here behaves like this if that, and this if that. And now what I can do is I can just say, okay, if x is this, then this equation, if x is this, then the mod function is just doing this. And this equation you can just write without the mod function, and you can solve it. Now the problem is, this is less than minus 4. And we were only interested if x was greater than minus 4 for this one here. So that's actually not a solution. However, if x is less than minus 4, we can replace x plus 4 modded with minus x plus 4, which is what I've done here. We can solve that, and this is less than minus 4, and so this is a solution, and that will be the one solution we have. Probably the most difficult question here, maybe on this whole paper, there was only 3 marks, is a line has equation y equals ax. So that's a line that goes through the origin with some gradient a. And it intersects this thing here at least once. Now this one does it twice, so this line would pass, this would qualify. Give a range of values of a. Now the easiest way to think about this is which lines would fail, right? You notice that any line with a negative gradient would pass. But what about a line with gradient 2? Now, this gradient here is 2, right? Because over here, the mod function is just being itself. It's being x plus 4, so the gradient here is 2. Or here I should be pointing out, really, maybe. So if you drew a line with gradient 2 as well, this would not intersect this anywhere, because it's parallel here, and then this goes off in a different direction. So a is 2 doesn't qualify. The moment you make even a tiny bit bigger than 2, even a tiny bit steeper, it will eventually intersect here somewhere, eventually, which passes, right? We need it to be at least 1. So if a is 2 or less, that will pass. However, if you make a less and less, eventually you get to this point here, where it touches this corner just there. And they prepped us for this. They told us, they asked us to find where that corner was. It's -5 down, 4 across. So the gradient is 5 over 4. So this gradient here is 5 over 4. So I think the times when it doesn't cross, when it doesn't intersect at all, is when you're between 2, including 2, and 5/4. 5/4 is 1.25. So when you're between 1.25 and 2, and I think you're allowed to be 2. I should have put an equal to sign here. You're allowed to be 2 because the parallel case never meets. So you're allowed to be 2. So therefore, which I actually changed there apparently. I don't know how I did that. So therefore, for at least one solution, we just want to avoid this case. So we want to be less than 5/4 or equal to, because that's a not strictly sign, or greater than 2. And in set notation, we just write it like this with the union symbol in between. And I think we're good to go. Question 12 then, so we want to integrate this. Usually we do integrals of y dx. However, y isn't written in terms of x, so we can't integrate with respect to x. So what we do very cleverly is we just write that as y dx by dt times dt. And y is in terms of t, dx by dt we can write in terms of t, and then we can just integrate with respect to t. So that's what we're going to do. Dx by dt is just 6 cos t, very simply. We know that the bounds of integration are just going to be when t is 0 and pi over 2. They told us that, so we can put that in. Y is just this, dx by dt is that, dt, we can expand that out. We can write sine 2t. I'm not going to bother doing this properly because we actually saw this a few questions ago. Sine 2t is just 2 cos t sine t. So we can replace that there, then we can expand out and we get what they want us to get. This is not the easiest integral to spot how to do immediately, but if I write it like this, maybe you guys will be able to spot it. This is just reverse chain rule, right? Because cos differentiates to something of the form of sine. It differentiates to minus sine, but that's okay. Because what I can just do is I can just say, okay, what must have differentiated to make this is cos cubed. Because the 3 would come down, drop down to a 2. Cos would differentiate to sine, and you'd leave behind a sine, cos squared. So this goes to this, and of course this becomes a 20, just because 3 times 20 is 60. And the minus here, just because to make up for the minus sign you'd actually get when you differentiate cos. So we end up with this. We put in pi over 2. This should be a pi over, this should be a 2, sorry, I just messed that up. I don't know why I typed a 4. That should be a 2. Anyway, that should be a 2. Cos of pi over 2 is 0, I believe. So that just goes away. You get a plus cos of 20. This is a plus here. You get a plus 20 cos of 0. Cos of 0 is 1, so you just get plus 20. That should be a 2. Apologies, that just threw me there for a second. Anyway, for this bit here, you've got this model here. Y is 4.2. So all I have to do, I think, is put in 4.2 into here and solve for t, which I can do fairly quickly. If I inverse sine of this, I get this and this. Now, this is bigger than pi over 2, but that's okay, because I have to halve it anyway. So I'll halve it, and then these two results are between these. Sorry, where did I get this from? Well, inverse sine of this, and you get this number here. And then that's like somewhere here. So I just did, well, that's 0.99 along here. So I just did pi minus 0.99, which is like 2.14. And then divide by 2, you get these two results. And just plug those two results into there, one by one, and you get your two corresponding x results. And then, of course, that corresponds to this coordinate and this coordinate. So this is at 5.2 across, this is at 2.8 across. We just do those two results minus each other to work out the length of the and we get this answer very roughly there. 13 then, so deduce the value of k. So the only way for this function not to really be defined is if we're dividing by 0. So log of x minus 2 can't be 0. If it is 0, then you get x as e to the power 2. So therefore k cannot be e to the power 2. Otherwise, you'd be dividing by 0 down here. Prove the differential is greater than 0. I already talked about my seething hatred of quotient rule. It will be a long day in hell before I ever do that. So what I'm going to do instead, just to really put my foot down on how much I hate quotient rule, is I'm going to do the same thing that I did earlier, which is I'm going to just try and write the top of this I'm actually simultaneously here avoiding doing either quotient rule or polynomial division in some ways, because I'm going to do that thing that I did earlier to avoid it. Well, I'm just going to write the top of this in this form. So this is like the top of this fraction here is like 3 log minus 2. Now this would make a minus 6 at the end. So I'm just going to take away another minus 1 to get 7. So I think this simplifies to this. Of course, I can split this here and I get this, and then these two things cancel and I get this. Of course, this is just log x minus 2 all to the power minus 1. This is very easy to differentiate because that goes away. The minus 1 comes down to make that positive, that turns into a minus 2. And then the derivative of this via chain rule is just 1 over x. And so we end up with this, which I guess we could write as this. Now, this is always positive because x is always positive, as defined here. So this is always positive. And this thing is never 0 because we just said that it can't be 0 ever. We got rid of that value to make it so. So this is either positive or negative, but you're squaring it. So it's always going to be positive. So you've got 1 over a positive thing times a positive thing, which is just going to be positive all the time. So just put a brief description of that. This question is quite tricky here, only for 2 marks, but it is quite tricky to find the right tactic. Look back at G here and say, okay, how do we make G positive? Well, either do a positive divided by a positive or a negative divided by a negative. So for this to be the case, either this is greater than 0 and this is greater than 0, or this is greater than 0, this is less than 0, sorry, and this is also less than 0. We need both things at both times. Sorry, we need both of these each time, and we can have either this case or this case. So here, just solve that. You need this, which leads to that. Now, this number here is bigger than this number here, because 7/3 is bigger than 2. So therefore, this is a bit like saying we need a to be bigger than 3 and a to be bigger than 2. But if you need that, then you just need this one here, right? Like, there's no circumstance in which a is bigger than 2 is actually going to help you out here. So we just need this to happen. And likewise over here, similar sort of thing happens. You solve these, you get this. And like this is like saying we need a to be less than 3 and a to be less than 2, which means you just need a to be less than 2. And so now we just need to be in both of the in either of these two cases, and we'll be fine for this here. Good. Oh, also slam on a greater than 0 because the input always has to be bigger than 0. So just slam that on there. I think that lost you a mark if you forgot to do that as well. Shame. Anyway, this question here, we talked about drawing a picture, I think in the very first or second question of this paper. Do it again. Think about what a circle must be to be only in the first quadrant, which is up here, and touch the x and the y-axis. It must look like this. But even more so, when you think about the center of this circle, its radius is clearly this, but that's also the distance to the center in the x-coordinate. And likewise, this is the radius, which is also the distance to the center in the y. So therefore, this coordinate is r if the radius is r. And so therefore, the circle is of this form. And I think that's hard to figure out unless you draw a picture. We can rearrange this, of course, and then just to find the intersections, we can shove this result into there. This is just some very boring algebra, which if you're desperate to watch me do, you can slow the video down and watch me do. I really can't be bothered to this very, you get this pretty quickly. Anyway, given the line is tangent to C, so tangent to C means b squared minus 4ac equals 0. So b is all of this, a is this, c is all of that. So we end up with this. Okay, so there's some more boring algebra, then we'll square this out, we'll multiply all this out, I guess, and eventually we'll get something good. You can divide by negative 16 here, although it's completely unnecessary because you can just shove this result into a calculator. You can put this into calculator as well, you eventually end up with these two results, which is what's going to be the answer. This should say R. I just typed X because I wasn't thinking. That should say R, apologies. That's a couple of mistakes on this paper here. I'm not very happy. This next question I just couldn't be bothered to do. I've put a video in the description of Eddie Wu teaching this to a class because it's just incredible. So just go watch that. It's better than anything I could put in PowerPoint whilst exceptionally bored. So just watch him do that in front of a class and prove this result. Anyway, given S10 is 4 times S5. So S10 is just what happens when you put 10s into this input here, and S5 when you put in 5s. S10 is 4 times S5. That means S10 equals 4 S5. Just replace with these two results. You can cancel the A's here, and you can cancel the 1 minus R's because A isn't 0 and R isn't 1, so you're not dividing by 0 there, so we just end up with this. And then, of course, we can rearrange this to get this eventually. And now, one way to do this would be to think of this here. If you replace y, if you say y equals r to the 5, you could say y squared equals r to the 10, because when you just square them, 5 times 2 is 10. Otherwise, you can just spot that this factorizes. You could think of this in your head if you wanted to as y squared minus 4y plus 3, and think, what does that factorize to? It factorizes to this eventually. just because this time this is, you add the powers to get 10, minus 3 of them, minus 1 of them make minus 4 of them, and then a plus 3 at the end. So either this is 0 or this is 0. This would, of course, lead to that. This would lead to this. But this is just 1, and we've already been said that r isn't 1. So we'll ignore that, and we'll say the actual solution is this here. 16 then. So usually when you do these questions for proofs of natural numbers, you just put all the natural numbers into two boxes, even and odd. So like this, and then, so firstly I'll do the evens. We can square this, and we'll get this, which is that. And now the problem is, this is neither obviously a multiple of 3 or one more than a multiple of 3. So what we actually have to do is we actually have to go back to the start and say, okay, how else could we box up the natural numbers rather than just evens and odds? And what we could do is you could say the next best thing maybe would be to say that they can either be a multiple of 3, one less, or one more. That takes in every single number, right? Because multiples of 3 come in every 3, you can either be on them one more or one less than them. So let's just do that. Let's just do the case if we're a multiple of 3. That's this case here. Just square that. That's obviously a multiple of 3. So that's this case here. So that's good. What if we said n was one more than a multiple of 3? We could write it like this, which we could then square. And we get this, which we could factorize to be this, which is clearly one more than a multiple of 3. So that's this case here. So that's good. And then the one less case, we'll square this. When we square this, this 1 becomes positive, which is the key. That should be a negative. Apologies. That should definitely be a negative. That's 3 mistakes. That should also be a negative. Obviously, I just did a lot of copying and pasting here. So that should be a negative. That should be a negative. That plus 1 is what matters, though. That makes this 1 more than multiple of 3. And therefore, you can just write QED according to the mark scheme. Just to make up for the rampant mistake making, I'll drop a knowledge bomb on you. QED stands for Quod Erat Demonstratum, which loosely translates to, in Latin to, or from Latin, to what is necessary to demonstrate has been demonstrated, or something like that. So yeah, apologies for those mistakes there, but I think that the idea was good. I got across the ideas and I did some teaching. So yeah.